Hello everyone. Welcome to the Essentials of Material Science and Engineering course. In this lecture, we will discuss about the atomic diffusion, specifically diffusion in solids. You might have observed that people migrate from one place to another or from one country to another. Similarly, birds and mammals also migrate when the living conditions are not suitable. In the same way, atoms, ions, or molecules also migrate. This migration is known as atomic diffusion. In very simple words, we can define diffusion as the net movement or transfer of atoms, ions, or molecules from one region to another. Basically, diffusion always happens from high concentration to low concentration region. Diffusion can take place in gases and liquids also. However, diffusion in solids is highly significant in materials processing. Many processes involving the treatment of materials often rely on the mass transfer on macroscopic or microscopic level. This happens within a specific solid or from a liquid or a gas or another solid phase also. This lecture discusses the mechanisms by which diffusion occurs, as well as laws of diffusion and the factors that influence the diffusion rate. Let's first have a look at some of the typical examples on how diffusion plays a critical role in understanding the behavior of the materials during or after the processing. First example is hardening or strengthening the surface of a metal by exposing it to impurities that diffuses into the surface region under controlled heat treatment. Such phenomenon is known as case hardening. Common examples of case hardening is carburization of steel. During controlled heat treatment, carbon from the surrounding atmosphere diffuses selectively through the surface and makes steel harder. The picture on this page is of a steel component that has been case hardened. As we can see in the micrograph obtained by using scanning electron microscope, the surface of the steel component, which is carbon rich, has different contrast than the bulk. You must also note that sometimes nitrogen is used to strengthen the surface of the steel. But this is very uncommon practice as compared with the carbon. Second example can be taken from the semiconductor industry. Semiconductors are often heat treated to improve their properties, which always involve atomic diffusion. In some cases, a decrease in diffusion rate is desired. In other cases, a higher diffusion rate is needed. For instance, the fabrication of integrated circuits, also known as ICs, involves the deposition of very thin and narrow conducting circuit paths on silicon wafers. These paths provide the passage of rapid current flow from one IC component to another. These paths are called interconnects. This figure shows the optical images of typical IC chip and SEM image of such interconnect. Let's now see which metal is the most suitable candidate to be used as an interconnect. We know that there are four very highly conductive metals. For example, silver, copper, gold, and aluminum. The values of electrical conductivities of these metals at room temperature are shown in this table. As we can see in this table, and if we ignore the cost of the material, then on the basis of these conductivities, we can say silver is the metal of choice for the interconnects due to its higher conductivity, followed by copper, gold, and aluminum. However, generally aluminum is preferred over silver, copper, and gold. Let's see the reason behind that. We must note that after these interconnects are deposited, the IC chip is heat treated, often as high as 500 degrees Celsius. If during this process there is a strong diffusion of metal into the silicon, the electrical functionality of the IC chip will not be suitable for device applications. As we can see in this figure, the values of diffusion coefficient D for these metals are given at 500 degrees Celsius. Here one can see that the diffusion coefficient for aluminum into silicon is about 3.6 into 10 raised to power minus 26 meter square per second, which is at least 8 orders of magnitude lower than the values for the other three metals. So we can infer that aluminum is preferred due to its lower diffusion coefficient. Another example is related to the electrical conductivity of the semiconductors, which can be improved by adding impurities. For example, for junction transistors like NPN or PNP type, two commonly used wafers are silicon and silicon carbide. Talking about pure silicon, which has lower intrinsic charge carrier concentration of about 10 raised to power 10 per centimeter cube at 300 Kelvin. This can be increased via doping. The introduction of impurity into silicon can be mostly achieved by diffusion or in some cases by ion implantation. Moreover, the proper functionality of the junction transistors also highly depends on the diffusion of electrons from N to P-type region or from P to N-type region respectively. Based on these examples, we can conclude that the study of diffusion mechanism and diffusion rates at atomic level is extremely important for materials scientists. Now let's understand the basics of atomic diffusion. We can demonstrate this with the help of our diffusion couple. In this example, we will consider two different metals. Let's say copper and nickel. If copper and nickel bars are joined together and then heat treated below their melting point, the copper and nickel atoms will migrate into their counterparts, as you can see in this figure. After the pair is cooled down, we can notice the formation of an alloy at the interface. It can be seen that both pure copper and nickel only exist at the two extremes of the pair. This result indicates that copper atoms have migrated or diffused into nickel and that nickel atoms have diffused into copper. The process by which atoms of one metal diffuses into another is termed as interdiffusion or impurity diffusion. It's interesting to note from the plot showing the concentration of copper and nickel as a function of position that there is a net drift or transport of atoms from high concentration to low concentration region. In addition, diffusion also occurs for pure metals, where all atoms moving around are of the same type. This diffusion is known as self-diffusion. This kind of diffusion is very common, but it is hard to see any compositional changes. The mechanism of diffusion in gases and liquids is based on random motion of molecules or atoms, also known as Brownian motion. However, the mechanism of diffusion in solids is very complicated. Now, we will discuss the mechanism of diffusion in solids from an atomic perspective. Diffusion in solids is the stepwise migration of atoms from one lattice site to another. It is a known fact that every atom in a solid is vibrating very rapidly about its lattice position within the crystal. In a sense, these atomic vibrations may be thought of as imperfections or defects within the crystal. These vibrations are shown in the figure on the left. Basically, the atomic vibrations are in the form of lattice waves or phonons and play a critical role in heat conduction. So here we can conclude that atoms in a solid are always in constant motion and rapidly changing their positions. The figure on the right shows random transfer of atoms from one lattice to another. Here, two conditions must be fulfilled for an atom to make such a move. The first condition is the availability of atomic empty adjacent site, and secondly, atoms must have sufficient energy to break the bonding with its neighboring atoms. Due to this, the displacement of an atom can cause some lattice distortion. Even at room temperature, a small fraction of atoms is capable of moving around, because now the magnitudes of the vibrational energy is sufficient to break the bonding. More importantly, this fraction increases with the increase in temperature. Specifically for metallic materials, two mechanisms are proposed for atomic diffusion. First one is known as vacancy diffusion, and another one is known as interstitial diffusion. Vacancy diffusion mechanism is shown in this figure. Vacancies are the defects caused by loss of atoms from their lattice sites. As you can see here, diffusing atoms and vacancies exchange their positions, but their motion is opposite in the direction. Both self-diffusion and interdiffusion can occur by this mechanism. However, the interdiffusion, the impurity atoms must replace the host atoms. The presence of vacancies is very important here because the rate of vacancy diffusion depends on the number of these defects as well as on the activation energy of this exchange. You must note that significant concentration of defects such as vacancies may exist in materials at higher temperatures. Let's have a break here.